Hello, I'm David, and this episode is all about code optimization. So, what exactly is code optimization? Well, it's the process of writing or rewriting code to run more efficiently or use fewer resources. And most often, but not always, those two goals go hand in hand. I guess the idea behind code optimization is to get every command in the program to do as much work as possible. In my last video, I talked about rewriting this extensive subroutine from my 24-digit 7-segment display into a much smaller one that would accomplish the same job but take up far less space. As this routine stands, it takes up 99 commands. That's 1/20th of the available space in the PIC16F882, which has 2K of program memory. Now, by using INDF and the FSR registers, we can reduce the size of the code from 99 commands down to just 31. So what is this routine doing anyways? Well, it's looking at 3 data bytes in memory that represent data that I want to show on the 7-segment display. First, we look at bit 7 in the byte and load W with the ASCII equivalent 1 or 0. Next, the data is stored in a memory array that represents the data that will actually be shown on the display. This consists of 24 bytes broken up into 3 8-byte arrays. I set up the display memory like this so I can show more than just ones and zeros. I can do messages like this one. Okay, so that's basically what this routine does. Just looks up each bit in the 3 different bytes and stores the resulting 1 or 0 ASCII character in the display memory array. Pretty simple stuff, really. Now, the optimized code is broken down into 2 subroutines: display convert binary and display convert binary store. Let's step through each of the commands and see what they're doing. First up is make select display underscore mem underscore display 1. This just makes sure that the proper memory bank is selected, and it is very important since I don't know where in memory the array will be placed. The compiler at compile time decides where that array is going to go. Because of the way I'm declaring the arrays here, the compiler has the ability to place them anywhere in memory that it sees fit. Next, we copy the contents of a variable named showWorking into W. This is the data that will be converted from a straight binary value into a string of ASCII characters representing the contents of this register. Next, W is copied into display underscore temp, which is the variable we'll actually be doing all the work on. The next command is key to this whole process. Move LW display mem display 1 is actually loading W with the physical memory location that the variable display mem display 1 starts at. Now that we have the data we need to work with stored in display temp and the starting address of the array display mem display 1, we can call the routine that is actually going to do all the work: display convert binary store. Yeah, I know it's a long name, but it's very descriptive. Now, remember when we call this routine, W contains the starting address of an array. So the first thing we have to do is tuck that into a safe place. And that safe place is the FSR register. The FSR register stores the address of another register in memory. And when we access the indirect F register, we'll actually be addressing the register FSR is pointing to. Next, we need to set up a counter. So the value 8 is loaded into the W register and then stored into display count L, which is a variable I'm borrowing from another routine. It's safe to do this since display count L isn't being used at the moment and isn't storing any critical information. Now we assume the bit that we're about to test is actually 0. So we load W with the ASCII character 0. Then display temp bit 7 is tested to see if it's a 1. If it is, then W is loaded with the ASCII character 1. Next, W is copied to indirect F, which actually copies the data to the address FSR is pointing to. Now it's time to update the FSR register so it's pointing to the next address in line with the command INDF FSR, F. Then the contents of display temp are shifted left 1 bit so we can test the next bit in line. Next, the value in display count L is decremented by 1, and if the new value is 0, then we skip the next command and exit the routine. If it's not 0, then we loop around and do everything again. Now that we are back in display convert binary, we repeat this process again for the variables show_register and show_temp. As you can see, by optimizing the routine, I've reduced the size from 99 commands to 31 commands. And when you're dealing with a microcontroller with very limited program space, this is a big deal. I hope you've enjoyed this quick look at code optimization and how you can take a large routine and just, by doing things a little bit differently, really reduce the size of it. If you have any questions, feel free to contact me. Take care and thanks for watching. Also, be sure to rate, comment, and subscribe.